So as we continue, okay, we have to take note that the assumption of Poisson vehicle arrivals also implies a distribution of the time intervals between the arrivals of successive vehicle, wherein arrival of successive vehicle, we're talking about time headway. So to show the average arrival rate, so we have here lambda. So lambda represents the average vehicle arrival rate, which is in vehicle per second. That will be equivalent to Q all over 3,600. Q is the flow in vehicles. So this is now the formula. This is now the formula for our average vehicle arrival rate. So therefore, if we're going to substitute now the equation of the average vehicle arrival rate lambda to our probability equation, we can have this equation. So this is now the probability equation showing to us the equivalent value for our lambda, which is Q all over 360. So if we're going to have now the probability for there will be no vehicle that may arrive in a time interval of length t. So we can have this equation. P, which is n is 0, so there is no arrival of vehicle. That will be equivalent equal to P, which is our h or our vehicle headway is greater or equal to our t. So that will be equivalent actually to e raised to negative qt all over 3,600. So the distribution of vehicle headway is known as the negative exponential distribution and is often simply referred to as the exponential distribution. So we move on to headways and the negative exponential distribution. So we move on to our example. Consider the traffic situation wherein in our previous example, we have given that we have a headway which is 360 vehicle per hour. Again, assume that the vehicle arrival are Poisson distributed. What is the probability that the headway between a successive vehicle will be less than 8 seconds? And what is the probability that the headway between successive vehicle will be between 8 and 10 seconds? So for this one, we have to take note that our expression gives a probability that the headway will be less than 8 seconds. So if the headway is less than 8 seconds, so we can have this equation, this expression. A probability that the headway represented by h is less than 8 seconds, so less than our t. So that will be equivalent to, this will be our equation, 1 minus e raised to q's of t all over 3,600. So we simply have to substitute our Q, which is our 360 vehicle per hour. Our T is 8 seconds, so we simply have the value 0.551. This is the probability that there will be a vehicle will arrive in less than 8 seconds. So what will be the probability? The second one, probability that the headway between successive vehicle will be between 8 and 10 seconds. So which means that we are going to identify here probability that the headway will be 8 and 10 seconds. So we simply have to have this expression, probability that our headway is h is greater or equal to t. So which means if we're going to have this one, when the headway is greater or equal to t, so that will be equivalent to, simply have to substitute. Q is 360. Our time is 10. We are going to have T is 10 since we have already computed when T is equal to 8. So for this one, we're going to have T is equal to 10 all over 3,600. So we get now the probability that the headway is greater or equal to 10, which is 0.368. So therefore, the probability that it will be in between 8 and 10, so which means that you have to subtract. So the probability that our h is in between 8 and 10 seconds, so we simply have to subtract the probability when headway is 8, when headway is less than 8 seconds and when the headway is less than uh, is greater than, rather, is greater than 10 seconds. So when the headway is greater than 10 seconds, we have computed that one. So this one is the probability that the headway is less than 8 seconds. This one is the probability that the headway is greater than 10 seconds. So therefore, the second question is, what will be the probability that the headway is in between 8 and 10 seconds? So which means headway is greater than 8. So that will be a probability that the headway is greater than t, which is actually 8. So that will be greater than 8 but less than 10. So this is the probability that our headway is in between 8 and 10 seconds. So which means we simply have to subtract the value for h, the probability when h is less than 8 and when h is greater than, when h is less than 8 and when h is less than 10. So which means that when the headway is less than 8, we have a value which is 0.551. When the headway is greater than 10, so the value is 0.368. So what will be the probability that h is in between 8 and 10 seconds? We simply have to substitute 0.551 minus 0.368 to 1. So 1 minus 0.551 minus 0.368. So the result here is 0.081. So this is the probability that the headway is in between 8 and 10 seconds. So what is the limitation of the Poisson model? So for this one, we have to take note that empirical observation have shown that the assumption of Poisson distribution traffic arrival is most realistic in highly congested traffic conditions. So meaning to say, our Poisson distributed model is realistic if there is a lightly congested traffic condition. As traffic flow become heavily congested or when the traffic signal causes cyclic traffic stream disturbances, other distributions of traffic flow become more appropriate. So which means that if there will be a heavy traffic condition, so some of the distribution or traffic flow model will be appropriate to analyze, to model the traffic flow instead of using the Poisson distributed traffic arrival model. So this is an illustration to us showing the exponentially distributed probabilities of headways greater than or equal to t, with q is equal to 360 vehicle per hour. So we have here time t with respect to the probability. So this is the flow chart. This is the graph when p is greater, when the probability when headway is greater or equal to t, which is equal to e raised to negative qt all over 3,600. Okay, now we move on to queuing theory and traffic flow analysis. So you have to take note that the formation of traffic queue during congested period is a source of considerable delay and result in a loss of highway performance. So under such extreme condition, queuing delay can account for 90% or more of a motorist total trip travel time. So if we're given with this essential in traffic analysis, so to develop a clear understanding of the characteristic of queue formation and dissipation along with mathematical formulation that can predict queuing related elements. So the problem for queuing is not unique to traffic analysis. However, basically, many non-transportation fields such as the design and operation of industrial plants, retail stores, service-oriented industries, and computer network must also give serious consideration to the queuing problem. So, in fact, the impact of queues on performance and productivity in manufacturing, retailing, and other fields has led to numerous theories of queuing behavior. So that is the process by which queues form and dissipate. So for this one, we're going to have now dimensions of queuing model. So basically, the purpose of traffic queuing model is to provide a means to estimate important measures of highway performance, including vehicle delay and traffic queue length. So such estimates are critical to roadway design. So we are talking about the required length of left turn haze and the number of lanes at intersection and control operation traffic operations control, including the timing of traffic signals at intersection. So we have to take note, of course, that if queuing refers to uh, it causes so much delay to motorists. Actually, queuing uh, it's not only it's not only on highways. There is a queue formation. It is also visible to retail stores, to bank. So somehow there is what we call a queuing problem, basically because due to congestion. So for example, in highway, due to heavy traffic congestion, queuing there is a problem uh, on queuing as on the queuing aspect. So same as with the retail store, the banks. So if there is a lot of people entering through that establishment, so basically there is a delays. The accountability for the delays is basically on the queuing aspect. So queuing models are derived from underlying assumption regarding arrival patterns, departure characteristic, and queue discipline. So the traffic arrival patterns were already explained previously, given an average vehicle arrival rate, which is lambda, two possible distributions of the time between the arrival of successive vehicles were considered. So those are equal time intervals and exponentially distributed time interval. So in addition to vehicle arrival assumption, the derivation of traffic queuing actually requires assumptions relating to vehicle departure characteristics. So particularly, the interest is the distribution of the amount of time it takes a vehicle to depart. So for example, the time to pass through an intersection at the beginning of the green signal, the time required to pay a toll at a toll booth, or the time a driver takes before deciding to proceed after stopping at stop sign. So another important aspect actually for queuing model is the number of available departure channels. So for most traffic applications, only one departure channel will exist, such as highway lane or group of lanes passing through an intersection. However, multiple departure channels are encountered in some traffic applications, such as toll booth or turnpikes at an entrances and then at entrances to bridges. So which means that in the consideration in the analysis or in of the aspect for queuing model, so another consideration is the available departure channel. So it's very important to have its consideration as the number of departure channels. So for example, in a toll booth, for example, uh, there are some there are different channels on toll booth on the departure area, on the exit area. And another final necessary assumption relates to the queue discipline. So in this regard, two options have been popularized in the development of queuing models. So the first one is the FIFO, which indicating the first vehicle to arrive is the first to depart. And the last one is LIFO, so indicating the last vehicle to arrive is the first to depart. So that is assumption in the queue discipline. So if you are in the assumption, the first one, if you are the first vehicle to arrive, you are the first vehicle to depart. And if you are the last vehicle to arrive, you are the first vehicle to depart. So queuing models are often identified by three alphanumeric values. So the first one indicates the arrival rate assumption, the second value gives the departure rate assumption, and the third value indicates the number of departure channel. So we are indicating here, we have our queuing model. So that is denoted by D, and we have here different uh, queuing model.